Hey guys, in this video we're going to be learning our next probability rule. And in this video we're going to be doing all addition when we compute these probabilities. So in the prior video, all of our operations were multiplication. So the last video was multiplication rules. And the scenarios where we used multiplications were what we can refer to as AND probabilities. So this thing had to happen, and then this thing had to happen. So you draw a red ball, and then you draw a yellow ball, or you roll a 5, and then you roll a 2, or you pull out the ace of hearts, and then you pull out a spade. So it was like 2 successive things or 3 successive things happening in a row. So in those cases, you multiplied. So today's going to be a little bit different. These are going to be addition rules, and the scenarios we're going to be using this we can refer to as OR probabilities. So what is the chances that you draw a red ball or a yellow ball? Or what are the chances that you pull out the ace of hearts or a spade? So it's this or this instead of this and then this. So that's the difference. So our addition rule for probability, just going to summarize that, is used in finding the probability that either we'll call event A or event B occurs. And the rule that we're going to use looks like this: probability of A or B. So if it was probability of a red ball or a yellow ball, we'd say probability of red or yellow equals the probability of A. So we could say the probability of yellow plus the probability of B, plus the probability of blue ball or whatever, minus, this is the part that might look different here. And the correct mathematic way you would pronounce that would be A intersect B. So the intersection of A and B. So you can think of this as sort of the probability of both. Probability of both a red and a yellow ball or whatever, maybe case. So what we're going to do is subtract that out. So we're going to subtract out the overlap. You can think of it as like the overlap. Because in some cases, let's say your probability of a king or a heart, we're asked to do that. Well, the probability of a king in a deck of cards is there's 4 kings out of 52 cards, plus the probability of a heart. Well, there are 13 hearts, so plus 13 out of 52. So that's like our probability of A plus our probability of B. But then we have to subtract out the overlap. So we think, well, is there any card in the deck that is both a king and a heart? And yeah, there is one. There is 1 king of hearts. So we're going to subtract out that overlap. Because if we don't do this, then that king of hearts gets counted twice. It gets counted here and here. So we're counting it double. So we've got to subtract out one of those. And that's what this is doing here. It's subtracting out the overlap. So that would give us our answer, which would then be 16 out of 52, or 8 out of 26, which is 4/13. Okay. So when we're talking about ORs, we're going to do the probability of the first thing plus the probability of the second thing, and then minus the overlap, if there is an overlap. So another example. In a college calculus class, 90% of students pass the first semester. So that's going to be referred to as event A. 85 passed the second semester, so that would be event B. And 80% passed both semesters, so that would be the A intersect B. What percent of students passed either the first or the second? Okay. So the way we're going to write this is probability of, let's say, first semester or second semester. We can abbreviate that, probability of first or second, equals, and then we would want the probability of the first, which was 90%, plus the probability of the second, which is 85%. And then we're going to minus out the both, the overlap. So 80% passed both. So 80% of them would be getting double counted. So we'd have to subtract out that 80%. And that would tell us how many passed either the first or the second. So when we do that, it comes out to 95%. So 95% of students either pass the first or the second or both, right? So let's say in this particular class, you needed to pass either one of the semesters and then pass the the final exam or something like that. So 95% students would still be eligible to pass for the year. Often we use a Venn diagram to represent this. A Venn diagram, if you remember, is just like two circles that overlap each other. Looks something like this. So if we called this circle probability of event A, and then we had another circle, and this blue circle represented the probability of event B, the overlap, which is this area in the middle, would represent the probability of A intersect B. So when we're doing this, if we're trying to find probability of A or B, we're essentially subtracting out this middle so it doesn't get double counted. Because when we do probability of A, we get it counted once. Probability of B, we get it counted again. So then we have to subtract out this area so it doesn't get double counted. But that would be what the Venn diagram would look like. You'll often see that in textbooks and things like that. Now there is a scenario, something that we're going to call mutually exclusive or disjoint. And this is actually an easier scenario because in this case, two events cannot occur together. So for instance, what is the probability that it's going to rain today or not rain? Well, those two things are mutually exclusive because it can't simultaneously rain today and not rain today. Only one of those could be true. So if that's the question, then the intersection of those two, the probability of A intersect B, would be 0 because there's no way it could possibly rain or not rain today. Or let's say you have big tub of balls and you're asked the probability of pulling out a red or a yellow. Maybe the probability of red is 1 out of 5 and the probability of yellow is 1 out of 3. Then you would need to subtract out the intersection. Well, is it possible to pull out both a red and a yellow ball? Well, no, because you're just pulling out one ball. It couldn't simultaneously be red and yellow, assuming they're solid the whole way. So then that intersection would be just -0, would be how you would calculate it. So these are kind of rare, but there is situations where we would say something is mutually exclusive, meaning one excludes the other. It can be given that way. Your book also uses the term disjoint, so kind of like separated or apart. Problem where this would be the case. Generally, you'll know that this is the case because there won't be they won't say like the probability of both occurring. So if that's missing, then you just assume it's 0. So in this scenario, let's say you're trying on jeans at Kohl's. Researchers have found that the probability of a pair of jeans being too tight for a customer is 0.3, and the probability of a pair of jeans being too loose is 0.1. The question is, find the probability that a given pair of jeans will be either too tight or too loose. So essentially, what's the probability that a pair of jeans is not going to fit a customer? Okay. So we were going to do probability of too tight or too loose. That's going to be the probability of too tight first, which is 0.30, plus the probability of too loose, which is 0.10. Whoa, sorry guys. Minus, now this is where the overlap occurs. Well, in this case, they didn't give us any other information about jeans being both too tight and too loose, and that's because, well, you couldn't have a pair of jeans simultaneously being too tight and too loose, right? If it's not going to fit you, it's too tight, then it's not going to be too loose. So those things would be impossible to occur together. They are mutually exclusive. So then we would just put -0. Or you could just not write anything, but I like to put the -0 just to remind you of the rule that there is no overlap there. So the probability of A intersect B would be 0, So then it would just be 0.40 would be the probability of it being too tight or too loose. So basically a 40% chance that a pair of jeans that you could try on are not going to fit. The Venn diagram for this will look a little bit different because there would be no overlap. This would be the probability of A over here and the probability of B over here. And they don't intersect each other. There's no overlap. So it's just one or the other. So these are mutually exclusive. This is what the Venn diagram would look like. Mutually exclusive events. No intersection. All right, we're going to go through and do some more. So first example, a sample of automobile dealerships found that 19% of automobiles sold are silver, so the color is silver. And also found that 22% of automobiles sold are SUVs. And 16% of automobiles are silver SUVs. So it's saying 16% are both silver and an SUV. So the first question is, are the events mutually exclusive? In other words, can these not overlap each other? Could you not have a car that is silver and an SUV at the same time? Well, the answer to this is going to be no, right? Because you could have a silver SUV, and that's what it's asked us. So they're not mutually exclusive. It's not either one or another, because it even gives us a sort of a both right there. So these are not mutually exclusive. It's a little bit confusing saying not mutually exclusive. Seems like there should be just a better word to say it, like they are inclusive or something. But the correct way would be saying no or not mutually exclusive. And you'll have a few problems at the beginning of your assignment where you just have to write mutually exclusive or not. All right, so what is the probability that a randomly chosen automobile sold is silver or SUV? So we're going to write probability of silver or SUV. I do want you to write this out when you do these problems. Don't just write the answer. You need to write out this probability of silver or SUV. So first probability of a silver is 19%. Probability of an automobile that's an SUV is 22%, so plus 22%. And then minus the overlap, which is 16% of all cars sold are silver SUVs. My car that I drive is actually a silver SUV, so kind of a coincidence. And do the math there, we would be left with 25%. So 25% of all cars sold at this dealership are either silver cars or they're SUVs or they're silver SUVs. Let's go look at the next one. Surveying couples in a city found the following probabilities. Probability that husband is employed is 80.85. Probability that a wife is employed is 0.60. And the probability that both are employed is 0.55. If a couple is selected at random, find the probability that at least one of them is employed. This is just a different way of saying either husband or wife, at least one, meaning one, the other, or both. So same question we've been asking. So let's go ahead and answer that part. So we would just say probability of husband or wife. Well, we would just take the probability the husband is employed, which is 0.85, plus probability that wife is employed, 0.60, minus probability of both, which is 0.55. And do the math there, and we're left with 0.90. So 90% of households would either have a husband or wife or both would be employed. So they would have one person employed in 90% of households. Which I guess you could say maybe the unemployment rate is 10% then, or something like that, at least per household. I guess you would also have to consider people that are retired as well, that they wouldn't necessarily be employed. The next question asks you, what is the probability of neither being employed? So probability of neither. Just think about this logically. If the probability that either one of them or both are employed is 90%, and the probability that neither of them would be employed, we just do 1 because 1 is certainty. That's the total amount of probability minus 0.90 or just 0.1. So 10% chance that nobody is employed, which we kind of already said. This is called the complement, is the technical term. The complement is always just 1 minus whatever the chances of it being true are. So chances of it not being true are 1 minus 0.9. There is one problem on your assignment that you do this. And I'll try to point that out to you. Okay, let's look at a deck of cards. One card is drawn from a standard deck of cards. What is the probability that it is an ace or red? Okay. So again, keep in mind this is different from the last video in that it's an or question and not an ace and then a red. It's an ace or a red. So that's the key term there. Or tells you addition rule that we're using. So a probability of ace or red. Hopefully you remember a little bit about how many cards of different suits and stuff there are. So the probability of getting an ace, first of all, think about how many aces there are. Well, there is 4 aces out of 52 cards. So it'd be 4 out of 52 plus a red card. Think about how many red cards there are. Well, there's 13 diamonds, 13 hearts. So total, half of the cards are red, so that'd be 26. Oops. Sorry about that. 26 out of 52. And just leave it as that out of the 52 for now. Don't try to simplify these until the end or else it'll be very difficult for you. So plus 26 out of 52. And then we need to think about the overlap. So probability of both a red and an ace. Think about how many red aces there are in a deck. Well, there's an ace of hearts and an ace of diamonds. So there's 2 cards that are both red and aces. So those are getting double counted in these because they're counted in both of those. So we're going to then subtract out 2 out of 52, which would then leave us with 28 out of 52. Do the math there. Remember when you add and subtract fractions, you just add and subtract the numerators. So that would be 4 plus 26 is 30, minus 2 is 28. You keep the denominator the same. And that can reduce to 4 goes in both 7 and 13. That's it. All right, next one. In a group of 35 children, 10 have blonde hair, 14 have brown eyes, 4 have both. If a child is selected at random, find the probability the child has blonde hair or brown eyes. So this should be pretty simple. Probability of blonde or brown eyes. Probability of blonde hair is 10. And we do it out of the total number, 10 out of 35. Plus brown eyes is 14 out of 35. And then minus the overlap is 4 of both. So minus 4 of 35. 10 plus 14 is 24. Minus 4 would be 20 out of 35. Reduce that. 5 goes in both of those. It'd be 4 over 7. And one more question. I think, yeah, one more. Oops. Sorry, I'm struggling here. All right, we've got 400 college students. 285 students are enrolled in either. So this one's going to be a little bit different, and there will be 2 questions like this on your assignment. It gives you this in a little bit different order. It says 285 students of these 400 are enrolled in either a math or science course. So this first statement here is actually the answer that we've been finding in all of the other questions. So we'll keep reading. It says of those 120 of the students, 120 are enrolled in math and 220 are enrolled in English. Determine how many students are enrolled in both a math and science course. So we're switching what we're asking here. It tells us how many are enrolled in either or, right? And then we're asked to find how many are enrolled in both. So in this question, it's actually asking us what is the probability of A intersect B, essentially? Because we're asked to find what is the probability of both. But it gives us the answer that we're generally trying to find. So if we were to sort of write out the original problem, the probability of either math or science, right, would be the general setup. And that would be the probability of math plus the probability of science minus the probability of both. This would be our general formula here. So if we just write this out and then just plug in everything it tells us, we can then figure out how to solve this. So it tells us the probability of math or science. That's the first thing there. It says 285. So we would say 285 out of 400 would be the probability of math or science. Equals the probability of math, which is 120 out of 400, plus the probability of science, that was 220 out of 400, minus the probability of both. We don't know that, and that is what we're going to try to find. So we're just going to look at this as sort of like an algebraic equation. Just view this, you could even call this x if you wanted to. That's what we're solving for. Basically, we just need to rearrange this thing around a bit. Let's go ahead and just, what I like to do, I don't really like negatives with my variables, so I'm just going to add that over to the other side. So I'm just going to add the probability of both over, just move it over to this side. So I've got 285 over 400 plus the probability of both, just rearranging my equation, equals, and then these two we can add together, 120 plus 220, which would be 340 over 400. And then we just need to subtract that 285 over to get the probability of both by itself. So minus 285 over 400 from both sides. And the probability of both then would be 340 minus 285, which would be, looks like 55 over 400. So there are 55 students enrolled in both math and science. There are two questions like this, like I said, on your homework assignment, where you're going to be doing the opposite here. Just write it out just like this, plug in everything it tells you, and then you're just going to be doing the same rearrangements. You're essentially just switching these two places, adding that over, and then subtracting the other one. So I'm just going to briefly go over that assignment really quick for you here. So in the first section of this assignment, you're going to be asked to tell whether these are mutually exclusive or not. So that's just going to be yes, mutually exclusive, or no, not mutually exclusive. Most of them are yes, mutually exclusive. So I'll let you figure those out. Then 2, 3, 4, 5, those are just going to be probability of, these are going to just be or probability. So this is either, which means or, right? This one, dead battery, or because of no gas. Number 4, Macon Expressway or Seaview Expressway. Number 5, probability that either man or his wife is college graduate. Number 6, this one is the probability of no breakdowns. So this is going to be like we did the 1 minus your answer. So you're going to calculate it like normal, and then you got to do 1 minus that. And then 7 and 8, these are like the last problem we just did, where you're trying to find the probability of both. So this one is a both. So this is like the last problem in the notes. And then what is the probability the married man will buy flowers? And so this is the both again. So this is like the last problem. And then number 9, when you try to figure that one out on your own, it just has basically multiples. So I think it's 3 it asks you about. So try to figure that one on your own. All right. And as always, reach out to me if you have questions.